Okay, so hello everyone. My name is Daniel Bedau. I'm with Western Digital, and I'm going to give you a very brief overview on solid-state nanopores and what the physical properties of the nanopores mean for realistic data storage applications. In principle, a nanopore is a very simple structure. It's a plate with a hole in it. You put an electrolyte, you apply voltage, DNA goes through, and you measure an electrical signal, and the electrical signal allows you to somewhat infer the sequence on the DNA. I'm saying somewhat. Performance has been very impressive on nanopores, but it does not really compare to the best competitive NGS approaches. On the other hand, nanopores have one very nice advantage. They can be made at the wafer scale. If you look at the inside of a SBS system, there's lots of optics in there, there's lots of mechanics in there, so that's nothing that can ever be miniaturized. You need skilled people to assemble this. It's very different. From that point of view, clearly the nanopore has some serious advantages. So I said it's easy. One downside, and the reason we are doing this, is that DNA is pretty small molecule. So we are talking about 2 nanometers diameter and one revolution per roughly 3 nanometers. So when you make a pore that has couple, let's say 5 nanometers diameter and 5 nanometers thickness, you're never going to read out an individual base. You're always going to read out a convolution over everything that's in this pore. And that's what we call intersymbol interference, because all these symbols, they interfere with each other. And that's clearly, as we just saw in the last talk, one of the challenges of nanopore readout. Also, the thing is small. This is much smaller than anything we make in microelectronics. Just to put this into perspective, I have a horizontal cut here through a NAND flash structure. You have deep pillars, and this is a cross section. I put a tiny piece of DNA to scale, and then you can't see it on this PowerPoint. Can't show it. So this is the zoom in here, and you see it's just tiny, and it's. This is really state-of-the-art fabrication for memory structures, and this is far smaller. So it's not easy to make these structures at all. So how do we do this? First, we start with a very thin film that defines the vertical structure. We cut a channel from the backside, and then we form a pore in the freestanding membrane. And all of these steps are pretty challenging, from the materials to making the pores. We just had a paper accepted here that was just published a few days ago, if you want to know more about different materials and different approaches here. Here's how it looks like in principle. It's relatively simple, but nothing is ever really simple in fabrication. You start with a wafer. There's quite a lot of lithography steps involved, and in the end, you have a little membrane, and all you need to do is put a pore in there. I have some with me later. If you want to see one, just find me. So we start with our membrane. We drill holes into it. Here we have a lot. We were testing how small we can make them. And by normal e-beam lithography, we can go down to around 10 nanometers. There are other techniques with dielectric breakdown where we can make kind of arbitrarily small pores down to single-digit nanometers. That's very impressive. It's a testament to the qualification of the fabrication engineers here. This thing has roughly the same aspect ratio as a cling wrap. So if you think you have a salad bowl with a cling wrap and you need to drill a hole through this, that's not easy. I'm very impressed by this. So then you take your pore. You put it in a flow cell. It's very manual. You pipe it in the solutions you want to test, and you put it in an amplifier, and you measure. And this is fairly slow. It's a lot of manual work there. What you get then is a lot of noise, and now and then you get individual spikes that indicate your DNA translocation events. Here you see a typical event, you see a spike, and what you see is here it's roughly twice as high. That's because the DNA folded over and formed a hairpin. So you see in this case we are nowhere near single base accuracy. The problem in the pores, and that's what people are working on, is the noise in these pores. This is a very complex system. You have physics and chemistry going on there. You have a trap state in the membranes that jump around. You have bubbles on the surface. And at the scale, bubbles don't really behave like you would expect bubbles to behave. It's not that you can knock it on the surface and they will just float up or so. That's, these are very strongly attached to the surface. And there's all kinds of chemistry going on. And this is a problem, especially at the low frequency. So this is 1 over F noise. It just goes higher and higher the slower you measure. Another problem at higher frequencies is the noise peaking. That is an electrotechnical phenomenon. There isn't really a way around this. You have the capacitance of the pore, and the amplifier, the voltage noise from the amplifier is just amplified by this capacitance, and that gives you noise that goes up with higher frequency, and then eventually the roll-off of the amplifier will bring the entire system down. And unfortunately, this is just in the range where we want to measure. Here's a typical curve of the noise. You see we have the 1 over F noise region. We have here a relatively flat region, and then it goes up, and then it goes down. Doesn't mean there's no noise. It just means we have no amplification here. And there's a lot of work going on, different materials, different surface chemistries, but no one has really found the perfect solution here. Another problem is controlled translocation. So if you work with, or if you take a hard drive apart, I wanted to bring one of it. I thought it's not a good idea to have a cut open hard drive on the flight here, but take it apart. It's really interesting what's in there. So you have these mechanical mechanisms, and they can position the head with nanometer accuracy. It's very, very tightly controlled. And in the nanopore, we have, let's see if this plays. No. You're not playing. Whatever. You can imagine. I'm sure you've all seen this. The DNA just wiggles through the thing, goes back and forth. It's very complicated. It worked before, but whatever. Okay. Doesn't matter. I think it's okay. If anyone really wants to see it, just find me afterwards. I have my computer with me. And yeah, so there's complicated interactions with the surface. You have there are some ideas to control the motion. In the end, that's what's done in the biological pores with Oxford, where you have a motor protein that the DNA threads through and that controls it. But that comes at a price. Now you have a relatively slow translocation that gives you throughput issues. Also, it's a different trade-off we're looking at here. We are not, of course, single base accuracy is interesting, but we need to make the system work overall. And if we need to have a little bit of coding, that's not a problem, because we need coding anyway. Also, in the solid state case, people really haven't found a good solution here. If you have one, I think that's an interesting area of research. So now I'm going to talk about hard drives, complete switch of topics here, because what I want to convey is that with hard drives we do things very differently. So for example, we've done all the nanopore work here, and it's done in the lab, on single little flow cells, but that's not how we do hard drives. We would never develop hard drives with a hard drive. Yeah, we have special tools here. It's an extremely expensive device. It's called a spin stand, costs a couple $100,000. And you can see the platter from the hard drive that sits there on an extremely precise spindle, much more precise than even the extremely precise hard drive. And you can really change all the parameters here. You can change gaps, distances, speed, and everything. You can read data multiple times. And we have a lot of these. Yeah, we have rooms full of these machines. And that's a big difference, because when we compare what's that one here? Yeah, when we compare what we can do. So, for example, in DNA, we are already very constrained with the data that we can write. Yeah, so we have the parity rules. We have problems synthesizing long homopolymer runs. We have what Robert has shown yesterday, issues with certain sequences that kill amplification. And in general, write errors are not really known. We have statistical knowledge, but not for the single molecule. It's very different for hard drive. So I have a picture here from a paper from Seagate that shows very nicely how you do these experiments. So you can just write a tone. Yeah, so simple 1010 sequence. You can write a pseudo-random sequence. And now it gets interesting, because we do the same sequence, but we write it at a higher frequency, and at even a higher frequency. And this measurement, measuring the response function as a function of the frequency, this is really one of the most basic measurements that everything else is built upon. With a nanopore, we do one read and then the molecule is gone. We'll never see it again. Combined with the error rate, it makes life kind of difficult. In the hard drive, it's very different. No, we can read as many times as we want, and we can read before we write. So in the back here is a read of a pristine disk. Then I wrote this a long time ago, so this is, just to put it in perspective, we measure density in tera dots per square inch as a patterned media. And you see here that there's a defect here, and there's a defect that was there before we wrote. So we can say there's something wrong with the media at this point. So this is not a write error. This is a media error, and this kind of thing we could never do with a molecule. So with the size, both of these systems, they are very size sensitive, and the critical dimensions are pretty much the same, which is maybe a good thing for gives us hope for nanopores. So we have these tiny holes. They are a couple nanometers large, and we make them. We cannot really change them. In the hard drive, it's very different. We can change the read gap during the measurement. There's a heater built in. If you look at this document here, you can see how it works. And this is done all of the time in your hard drive, and it's permanently being optimized. So actually, hard drives, they have a lot of theory behind them, so we understand magnetism very, very well. And we can do many measurements that are consistent. So for example, I talked about this gap here, and what we know is that the frequency response changes with this gap. There's a really interesting historical article here from the 1950s just showing how much this goes back from the Bell System Technical Journal, which is really interesting to read. And they show this. And so now we can measure the gap, the size, by measuring the frequency response, which we can't do for nanopores because we cannot do a frequency measurement here. And that's very unfortunate because, again, everything builds on this. And we have this excellent measurement here that gives us very, very many points that we can all cross-reference with each other, and we see if our model makes sense. With the nanopore, we can measure the resistance, and that's all. And we cannot get anything on the shape out of the thing. Noise, I talked about that big problem. We have some idea where it comes from, but not really the fundamental level of understanding that we have for magnetism. Again, magnetism, it's extremely well understood down to the level of what single atoms do. Here's an interesting article from one of my colleagues. What he does is he is writing the same data many times into different spots, and then he reads back every spot again many times, and that way you can separate write and read errors and get all kinds of information. These are the kind of sophisticated experiments that we do to characterize recording systems, and all this still needs to be done for the DNA channel in general. How am I time-wise? Good, perfect. So I have a table here. Want to make a little bit of a comparison. For some of these points, certainly it's a bit difficult to make a comparison, but I want to give you an idea what we deal with in magnetic recording systems. I mentioned the spacing, the measurement of the dimension. In the hard drive, we do it what's called the flawless spacing from the Bell System Technical Journal article. In the nanopore, we just do the ionic current. There's a single measurement. There's no consistency. You cannot see if the pore is cylindrical or conical or this, or has any other odd shape. And don't think about making taking TEM images, because that's really difficult, expensive. What's really important, also measuring the frequency response, because in the end, that's the key measurement that tells you how much density you can write. Super easy in the hard drive. A nanopore, well, not completely impossible, but very challenging. Media tests, so the hard disk drive media, they're tested with every surface analytical technique on the planet. Yeah, we have a whole building full of all these tools. Of course, with a nanopore, there isn't really a medium. No, the data is a medium, so there isn't really much to test if it's good or not. We have the geometry. We can tune the thing on the fly in the hard drive, and that actually happens. In the nanopore, we can't tune anything there. Write error rate, read error rate, again, it's important to separate these. The problem is, and this is not specific to nanopores, this is the case for any molecular storage application. Of course, there has a fairly high write error rate, certainly much higher than what you have in a hard drive. But you cannot really measure it. You can do ensemble measurements, but you cannot say for single molecules where the errors are, and that's a big problem. Reading is the same. How do you measure the read error rate if you don't know if the molecules have been written correctly or to what extent they have degraded? The cross checks, again, we don't want to trust single measurements, and we need to work really hard there to build a better measurement system of many cross-reference measurements. And just in the end, let me add this here, there's a lot of things that go on in a drive that no one here, other than my secret colleagues, would even think about. So if you have a drive at home, the thing collects hundreds of megabytes of data over its lifetime, just checking itself. These are very complicated systems. There's a lot of stuff going on there. So with that, I would like to conclude. Clearly, nanopore, the main problem is the noise reduction signal improvement. As far as data storage is concerned, the big problem is to develop optimal channel models or optimal encoding schemes. We need to understand how the underlying channel works, and we don't really understand this. We don't have good channel models, we don't have good physical models, and most importantly, we don't have any good measurements to do these things. I showed you the spin stand. Here's again, this cool article. You see you have this pivot point here where they could lift the head of the disk. So this was before they had nanometer spacings. Today this wouldn't work anymore. But this is really what we need, yeah? And cost is not an issue. Like I said, we pay hundreds of thousands of dollars for a single spin stand, and we have lots of them. The problem is we need a way to do proper measurements and do proper characterizations. And on a single cell, in a flow cell, that's not going to be sufficient. So what we need to do is, on the chemistry side, we need to create molecules that help us getting better channel estimates. So we need to create something that corresponds to these tones, something that has long homopolymer runs, maybe something that's not DNA, because DNA is not such a great molecule, to be honest. It's not too stable in the aqueous environment. So maybe there's something else. For the theory side, we need better channel estimators, and we need something that can work with the data that we produce from these ensemble measurements, because we cannot take a single molecule and measure it 100 times what we really want to. what we need tool-wise, we really need something like a spin stand for DNA storage. And that's really important because that's what we need. And yeah, in the end, we should look at other recording techniques, magnetic recording, what have people done there. And yeah, we should keep the discussion going. My email is there. I have some pores with me in case anyone wants to see them. And yeah, please reach out to me and let's discuss this. It's a very, very interesting topic.
Thank you, Daniel. That was a great presentation. Question, come on.
Daniel,
yes.
Thanks, Daniel. At least it was very encouraging to have a solid-state nanopore coming soon. No, just my question is how many years it took to develop the HD? Maybe you talk about a paper in 1950, so I would say 75 years.
So my colleagues developed the first one in 1956, I think, the RAMAC.
And how many, I mean, that's why how long it took to develop and to get the one that we have today, and when has been created the first nanopore is quite very short, and strong believers on technologies. So I believe that technology will come to help you to change your your presentation, and maybe seeing that maybe next year we'll have a solid-state nanopore.
Yes, working on it. No, it's a good point, and it's before we had hard drives, we had tape and we had wire recording. So the magnetic recording theory goes back 1900 something. It's a lot of, and the problem is you don't really learn about these things because obviously we don't talk about it. It's all internal knowledge. It's not that you can get a book and read about how to characterize a magnetic recording system. All this is decades old, what's available.
I have just a quick question. Noise is a main challenge according to you. What about pore blocking? Any particle larger than 10 nanometer will obviously block the nanopore. So how you deal with this?
With different sizes.
Yeah.
So this is, it's a challenge. No, if you can make them smaller, the problem is you're limited with the film thickness. Now we say, hey, let's take graphene, but graphene is really not nice for surface with water. It has many of these problems, much worse than silicon nitride, typical material. Also needs to be freestanding, and also needs to be produced at scale. And these 2D materials, they make tiny flakes they put somewhere, but we want to have something we can make on full wafers. But people work on them, and they have good results on the 2D materials.
Okay, thank you.
Hello, Lisbeth from IMEC. Very nice to see the progress. You started your presentation by comparing to biological nanopores and how many bases are in the pore, and that will determine in the end resolution. But how thin do you think a solid-state nanopore could you make, and how does that affect the noise?
So that's, of course, that's a hard question. No, you know that as well as I. So just to throw out some numbers here, when typically these membranes, we can go down to maybe 10 nanometers, and below that you get all kinds of stability problems, or they break. Probably you can make it, push it a little more. Maybe some single-digit nanometers, I would say that's where it probably ends. Maybe you can make something that's locally thinned. It's not an easy lithography thing, but again, you know that much better than I do.
Why are you working on this?
It's interesting.
Well, but does Western Digital just do interesting things? Do you have a commercial ambition?
Well, certainly.
And what is the state of that commercial ambition?
I can't speak on that. It's a good question.
Daniel,
we've seen glass nanopores yesterday, and the fact that and there are many publications where it's possible to detect structures on DNA rather than single bases. Do you think this kind of approach is mandatory for using solid-state nanopore to detect some signals, so maybe the structure encoding would be more suited than the base encoding, for example?
So this is a hard question again. So we have the biological pore, and it has many advantages. And in the diagnostic field, why would you want this if you can make the biological pore that are really superior from the signal point of view? How far we can push this, I'd say it's too early, because we don't have any of this data. And without any of this, we cannot even optimize. And again, we don't really know what the problems are. My guess would be probably we need some kind of encoding, but how large? I'd say that's a really pressing question, and I don't have the answer, but I really wanna know this. So if anyone has a solution, please send me an email, and let's discuss this.
Then I have one more question, because second thing, you have the application for life science that you want to know all the bases, but when you use the hard drive, you read just 0 and 1. So can we make pores that read 0, 1 or 0, 0, 0, 1, 1, 0, and that big, and it's something that, you say that the limitation is the size, it's too big, and we can do a lot of modifications of DNA, and
yes,
proteins are big, or is it something that you're exploring?
Yes, and I think that's a good approach. It's very challenging, because now we need to optimize this entire system. So we need to optimize the physics of the pore, we need to optimize the readout, we need to optimize the chemistry together with the system design, and for example, the ECC. And this is very difficult, because the ECC, it's a very manual process, so there isn't a way to look at this whole system globally and just optimize all the parameters at the same time. And what I would say the step to eventually go there is to have better models, because when we have better models, then we can simulate the system, and then we can tweak everything. And we are nowhere near there.
If there is no more question, we can just jump to the coffee break and keep going the discussion, right? Again, thank you so much for this afternoon session, and the speaker for the last presentation. It was great session. Thank you again.